Hi everybody, welcome back. I hope you had a nice weekend. Today we're going to be chatting about just a couple of topics that are going to come up in class. First one's motion on a ramp. So motion on a ramp is really a special case of constant acceleration motion. In the slide, one of the things that I like about this slide, I like about this figure, is it really sort of emphasizes that this is a geometry problem, okay? If you're having a hard time figuring out how to make sense of that, where that angle theta comes from, make sure that you either, take a close, hard look at it, or come and chat, okay? So in this case, we imagine the block sliding down the incline, and we've organized our coordinate system so that x points down the incline. I find that very useful. I usually do that. The direction of the acceleration is going to be determined by your sign convention. That's really important. And so don't forget that. This is really, again, just a special case of constant acceleration motion. Once you find the acceleration, then we can use our kinematics equations, just like we did before. So another topic was projectile motion. Now, we don't have a lot of problems. I don't think you have any problems today. So what we're going to do in class is we're going to spend some time working through a strategy to solve a particular problem. Now, as you read, take a particular look at figure 3.34. I think that's particularly good because it demonstrates for you what would happen if there was no gravity. Okay, so when we add gravity, something very specific happens to the motion. And I want you to pay particular attention to some of the conceptual ideas. One of the most important things, as you look at this slide, is that the acceleration always points straight down. It's constant. It doesn't matter where we are in the motion. The value of the vector analysis that we've been working on here is that once we recognize that the acceleration is a vector, that it points, and it only points downward, we deconstruct the problem into an x and a y problem. So in this case, the acceleration in the x direction is 0. The acceleration in the y direction is minus g, but they're both constants. Although the motions occur simultaneously, they can be analyzed separately. The thing that connects the two directions is the time. Don't forget to organize your problem-solving strategy. Prepare. In this case, I would organize variables, both x and y. What do you know? What don't you know? Organize. When you work to solve the problems, sometimes it helps to write down the kinematics equations. I'll sometimes do that if I'm not quite sure how to solve the problem. Maybe I will work through the number of equations I have, the number of unknowns that I have until I can get them to match up. And again, try to stay organized. As you assess your solution, again, bring intuition to bear whenever you can. Sometimes we can't, but do an experiment. Okay, throw something up in the air, right, to get a rough idea about whether or not if you have to calculate the time, if it makes sense. So the last topic here is relative motion, and I will admit relative motion can be really tricky. Now, I think that equation 322 is okay, but I usually don't rely on that. I think about my intuition. Problems 360 and 361 are also really good. I would strongly encourage you to work those problems. But there's a particular technique that I just wanted to emphasize in visualizing these relative motions. So you're going to do a problem with a kayak. So the kayak is trying to go across a river. We have some coordinate system. We have a coordinate system. North points up, east points, east. Now, there's a tide, and the tide points this way. So what I do is I call this the velocity of the tide, and it points directly east. Now, I want my velocity to travel north. So my net velocity looks like this. That's what I want. So if you want to visualize what the kayaker has to do, well, this vector plus whatever the kayaker is doing has to equal this one. So that vector, I'm going to do it in purple. This has to be the velocity vector for my kayak. Try to use that as maybe a nice starting point for you. And then, of course, this is a vector, we can break it down into components. Come chat. about this, but try to work through those problems. I think that they are particularly good. But come to me with any questions.